lot of students made the following mistake. They needed to get both the comparison of the surface area for the two trials. So we have a difference in surface area in terms of the particles, but they also needed to talk about the collisions. And so what happened is that sometimes students did not get both points because they might have talked about collisions but didn't mention the surface area, or they might have talked about the surface area but didn't mention the collisions. So I'll show you some sample student responses from question 3, part C, from the 2023 AP Chemistry free response questions. So let's take a look at this student. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 5.1 to 5.3. As you can see on this slide, these topics fall under Unit 5 in the AP Chemistry curriculum, Kinetics. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 5.1, Reaction Rates. Here are some essential knowledge statements from the AP Chemistry course and exam description. The kinetics of a chemical reaction is defined as the rate at which an amount of reactants is converted into products per unit of time. The rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation. And the rate of a reaction is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. Now it's time to move on to the practice for topic 5.1. This is question 1. Now, I had just mentioned that the rate of the reaction is influenced by reactant concentrations, and that's exactly what we see here in question 1. So we are given a table with information for 3 different trials of an experiment, and we are given a balanced chemical equation involving solid copper reacting with aqueous nitric acid, which has the chemical formula HNO3. It says a student placed 1 gram samples of solid copper in excess aqueous nitric acid of various concentrations, as shown in the table above. The time required for each reaction to go to completion is recorded. And as the concentration of nitric acid increases from 1 molar to 5 molar to 10 molar, which of the following is the expected result? Now, if you look at the 4 answer choices, we can see that the words or the phrases are time of reaction and rate of reaction. So if we have a higher concentration of reactant, that would lead to more frequent collisions between reactant particles, and that would result in a faster reaction rate. So the correct answer to question 1 is either choice B or choice D, and they both say that the rate of the reaction increases. But the time required for the reaction to go to completion is going to be shorter if there is a faster reaction rate. So we are expecting a shorter time of reaction, and that makes the correct answer to question 1, choice D. The time of reaction decreases and the rate of reaction increases. So hopefully that is a very straightforward question, that when we increase the concentration of a reactant, it does lead to a faster reaction rate, and in this case, a shorter time of reaction. Now let's take a look at question 2, which involves the stoichiometry of a balanced chemical equation. So in question 2, it says the following. Propane, C3H8, reacts with oxygen gas to produce carbon dioxide gas and water vapor as represented by the equation above. And at a certain time during the reaction, the rate of formation of carbon dioxide gas was 0.024 moles per liter per second. So that's the unit of concentration, moles per liter, and then per unit time. So you could say molarity per second or moles per liter per second. Now the question is asking about a different chemical. So we're given data for carbon dioxide, and it says, what was the rate of formation of water vapor at the same time? So again, we're going to use the stoichiometry of the balanced chemical equation to convert the rate of formation of carbon dioxide into the rate of formation of water. So I'll start with the number that I was given, 0.024 moles of carbon dioxide per liter per second. And now I'll take a look at the coefficients for carbon dioxide and water. And you can see that would be 3 and 4. You'll notice that I put moles of carbon dioxide on the bottom because that is the unit I'm trying to get rid of. And I put moles of water on the top in my conversion factor because that's the unit that I'm trying to convert into. So in terms of 3 and 4, it's going to be 4 moles of water produced for every 3 moles of carbon dioxide produced. So that's going to be a ratio of 4/3. Now, when I pick up my calculator, it's going to be 0.024 times 4 divided by 3. And then that gives me a numerical answer of 0.032, but what are my units? Now it's going to be moles of H2O per liter per second. So I have just determined the rate of formation of water at that particular time in the reaction. So the correct answer to question 2 is choice C, 0.032 moles per liter per second for the rate of formation of water at that particular time. Now, before we take a look at question 3 in this packet, I'd like to show you an example of a question that's very similar to question 2. And this came from the 2024 free response questions, and I will make sure that there's a link in the video description area to both this particular set of questions from 2024, as well as the scoring guidelines for these questions. And the specific question that I'd like to take a look at is part B of question 6. So I'll get a closer view of the text of this question. It says, at a certain point in the reaction, and here you have a balanced chemical equation, the rate of disappearance of NO2 is determined to be 6.52 times 10 to the negative 7, and the units are molarity per second. And so the question asks, determine the rate of appearance in molarity per second of oxygen at this same point in the reaction. And so, just like we observed in question 2, if you need to convert the rate of disappearance or the rate of formation of one chemical into the rate of disappearance or the rate of formation of another chemical within the context of a balanced chemical equation, you will need to use the coefficients. So the first thing I'm going to do is notice that there are 2 moles of NO2 consumed for every 1 mole of O2 produced. So I'll start with 6.52 times 10 to the negative 7, and my units are molarity per second, which I can write as moles per liter per second. Now, if I want to put NO2 into this calculation, but then come out with O2, I know that there's going to be either 2 and 1, but do we multiply by 2 or do we divide by 2? Now, you might know exactly what the correct setup for this calculation is. However, don't guess. When you have very simple math like this, always set up a conversion factor with the correct units based on the coefficients from the balanced equation. So it is going to be 1 mole of O2 on the top and 2 moles of NO2 on the bottom. And we do have this calculation of 6.52 times 10 to the negative 7 divided by 2, and we get 3.26 times 10 to the negative 7, but now my units are moles of oxygen per liter per second, or you could say molarity per second for the rate of formation of O2. So even though the math was very simple in part B of question 6 on the 2024 AP Chemistry free response questions, you can still make a careless error if you try to do too much in your head or you're not using units in the setup for your calculation. Now, here is the official scoring guidelines answer for this question, which, again, they do use the correct setup, and you can see the correct answer. And now I'll show you a few sample student responses. So for this sample student response, it says that in part B, the point was earned for the correct calculation of the rate of appearance of O2. So the student says, both in words and in the setup for their calculation, as 2 moles of NO2 disappear, 1 mole of O2 appears, and then they show the setup for their calculation, and they get the correct answer. Now, I think this student assumed that the stoichiometry was not relevant or important, so they wrote for their answer that the rate of appearance is the same as the number that they were given. So for this student, they did not earn the point because they did not take into account the stoichiometry of the reaction. And this next student, not only did they get the wrong answer, they didn't show their work. They didn't show the setup for their calculation. So I'm not sure exactly what they did, but I took a guess. And based on the number that they got on their calculator, this is what I think they did, because mathematically, if they took 6.52 times 10 to the negative 7 and they multiplied by a ratio of 2/3, then they would get the answer. Again, the incorrect answer that they wrote. So in part B, the point was not earned for an incorrect calculation of the rate of appearance of O2. But again, the important thing is there was no supporting setup shown. So always show your calculations, not only to help you set up the strategy for solving the problem, but in order to get credit for your calculation, you must show your work. So again, this was the answer to question 2 of this packet. It was choice C, and I just give you those comments. Always show the setup for your calculations, and even when the math is simple, it is a good idea to show your units in the setup for your calculations. It will hopefully increase the likelihood that you get the correct answer. All right, now let's go ahead and take a look at question 3. In question 3, we are given a balanced chemical equation. We're also given a data table from an experiment, and it says that a sample of solid CaCO3, which is calcium carbonate, is combined with a sample of aqueous HCl, which is hydrochloric acid, as represented by the equation shown above. Details from the experiment, including information about the reactants and the time required for the reaction to go to completion, are given in the following table. So we can see that the only significant difference between trial 1 and trial 2 is the particle size of the solid calcium carbonate. We have a fine powder that's used in trial 1, and then we have a large chunk of the solid in trial 2. And you can see that there's a shorter time of reaction for trial 1. It's only 67 seconds. And there's a longer time of reaction for trial 2. It's 342 seconds. So trial 1 is a faster reaction rate. Trial 2 is a slower reaction rate. Now here comes the question. It says, the student was asked to explain the reason for the difference in the reaction times for trial 1 and trial 2 based on the reaction conditions and the collisions that occur between particles. Now, the student wrote the following response, and then it says the student's response is incomplete. Now, before we look at the details of the student's response and what they left out, I'm going to mention that there is another AP chemistry exam that I looked at when I was preparing this question. So earlier I showed you an example from 2024. This is question 3 from the 2023 AP Chemistry Free Response section. Now, earlier I showed you question 6 from the 2024 AP Chemistry Free Response questions. This is question 3 from the 2023 AP Chemistry Free Response questions. And I'm focusing on a table which has a lot more trials. So I modified this particular question for the one that I wrote for this packet, for this episode of AP Chemistry Review and Practice. But go ahead and take a look at the question. You'll see it's very similar. It says, based on the reaction conditions and the collisions that occur between particles, explain the reason for the difference in the reaction times. And you can see that one of them is small chunks, so smaller particles would be larger surface area. and the other is a large chunk of solid. So again, we see a similar kind of setup for the one that we're working on in this packet. But the reason why I wrote this question is because a lot of students made the following mistake. They needed to get both the comparison of the surface area for the two trials. So we have a difference in surface area in terms of the particles, but they also needed to talk about the collisions. And so what happened is that sometimes students did not get both points because they might have talked about collisions but didn't mention the surface area, or they might have talked about the surface area but didn't mention the collisions. So I'll show you some sample student responses from question 3, part C, from the 2023 AP Chemistry free response questions. So let's take a look at this student. They said trial 3 had a greater reaction time because it was with the larger chunk, which would make the reaction time slower than that of the smaller chunk. Now, did they earn the point for surface area or collisions? Turns out, no, they didn't earn either of the points. It says in part C, the first point was not earned because the response makes no reference to surface area. And the second point was not earned because the response makes no reference to increased collisions between the particles. So on the AP Chemistry exam, if you are given guidelines such as based on the reaction conditions and the collisions, or based on Coulomb's law or principles of atomic structure or intermolecular forces, it's always good to mention the specific things that are being asked for in the question. All right, so this student did not earn either of the points. Now take a look at this next sample student response. They earned 1 out of the 2 possible points. So they said the larger the particle size, the less surface area of the molecule is exposed to the reactant, HCl. So the reaction time for the large chunks of calcium carbonate is greater than the small chunks because HCl is able to react with only the surface area of calcium carbonate, taking longer to expose more of the calcium carbonate to HCl. Did they get the surface area point? Yes. In part C, the first point was earned for correctly relating the calcium carbonate particle size to surface area. However, the second point was not earned because the response makes no reference to collisions between the particles. And now let's take a look at another student response that did earn both of the points in part C. So they say, although the concentration of HCl was the same for trials 2 and 3, the smaller particle size of trial 2's smaller chunks compared with trial 3's large chunk, increasing the surface area of calcium carbonate, thus increasing the number of calcium carbonate exposed to, and there's that word, collisions with HCl particles, and increasing the reaction rate for trial 2 as more effective collisions can occur at a time, decreasing the time for the reaction to go to completion. So in part C, the first point was earned for correctly relating the calcium carbonate particle size to surface area, and the second point was earned for a correct explanation relating increased surface area to increased chances of effective collisions. So hopefully you can see why I was inspired to write my version of this question for this episode of AP Chemistry Review and Practice. I was inspired by a common mistake that was made on the 2023 AP Chemistry exam that was relevant to topic 5.1. So now back to this question. It says the student's response is incomplete. They said, in trial 2, a large chunk of solid calcium carbonate is used. In trial 1, a fine powder of solid calcium carbonate is used. Compared to the fine powder, the large chunk has less surface area exposed to the reactant solution, aqueous hydrochloric acid. Therefore, in trial 2, it takes a longer period of time for the solid to react completely. And hopefully you can see that the reason why their response is incomplete is because they didn't talk about collisions. So it says, write 1 to 2 sentences that should be added to this response in order to address both of the guidelines that were given to the student. So again, as long as you mention something about increasing the number of collisions or the frequency of collisions, then you would earn both the first point about surface area and the second point about the collisions between the particles of the reactants. All right, now let's take a look at question 4. In question 4, we are given a balanced chemical equation, and it says substances Q and X react to produce substance Q2X3 according to the equation shown above. A chemist adds 24 moles of gaseous substance Q and 20 moles of gaseous substance X to a previously evacuated, sealed, rigid 4-liter container. So part A says, calculate the initial concentration of X in units of moles per liter in the reaction vessel before any chemical reaction occurs between Q and X. Now we have 20 moles of X in a total volume of 4 liters. And since the units of concentration are moles per liter, all we have to do is take 20 divided by 4. So 20 moles of X divided by 4 liters, that gives us a concentration of 5 moles per liter. So that's the answer to part A. Now we have a graph to examine in part B. It says the chemist records the concentration of Q and Q2X3 as the reaction progresses. The data are shown in the following graph. So if I start with substance Q, it begins with a concentration of 6 moles per liter. We can see that that's the label on the y-axis, is concentration in units of moles per liter. And it doesn't go down all the way to 0, but it does go down to a concentration of 3 molar. So we have an initial concentration for substance Q of 6 molar, and then we have a final concentration of 3 molar, and that's after a time period of 30 minutes. So the concentration of that reactant decreased from 6 molar to 3 molar. Now, since Q2X3 happens to be a product, then at the beginning of the reaction, there was no Q2X3 product, so its initial concentration is 0. But after 30 minutes, now its concentration is somewhere between 1 and 2. Looks like it's exactly halfway between 1 and 2 on the y-axis. So that would be a concentration of 1.5. So now we still have to do something with substance X. However, we can learn something very important about the stoichiometry just based on these two substances. So it says, notice on this slide that the change in concentration for Q, and that would be from 6 to 3, so that's a change of 3, is twice as much as the change in concentration for Q2X3, and that would be a change of 1.5. So why is the change twice as much for Q compared to Q2X3? Because look at those coefficients. The coefficients are 2 and 1 for those two chemicals, so that change is connected to the stoichiometry. So for every 2 moles of Q that are consumed, 1 mole of Q2X3 is produced. So that 2-to-1 ratio in the coefficients relates to the change in molarity in terms of the graph. Now, we didn't look at substance X yet, but let's go ahead and look at substance X. Remember that in part A, we already determined that the initial concentration of substance X is 5 moles per liter. So I'm going to put a 5 right there on the graph at time 0. Now, based on the 3-to-1 mole ratio for X and Q2X3, because I can see a coefficient of 3 next to the X, and it's a coefficient of 1 understood next to the product Q2X3. So based on that 3-to-1 mole ratio, which comes from the coefficients, we would predict that the change in concentration for X should be 3 times as much as the change in concentration for the product Q2X3. So what's 3 times 1.5? Well, 3 times 1.5 is 4.5. So we would expect that the final concentration of X would be 5 minus 4.5, which is 0.5. So now I'm going to go ahead and connect those two dots, those 5 molar at the beginning and 0.5 at the end after 30 minutes. I'm going to connect that with a smooth curved line. And now I've just answered part B of this question. So on the graph, sketch a single curve that represents the concentration of X as the reaction proceeds from 0 minutes to 30 minutes. Your curve should reflect the rate of change of X as compared to that of the other substances in the reaction vessel, and the initial concentration of X, and the concentration of X at 30 minutes. So that's what I'm showing. that substance X has an initial concentration of 5 molar, and then based on the fact that there's that 3-to-1 ratio between X and the product Q2X3, the change in concentration for substance X is 4.5, which is 3 times as much as the change in concentration for that product Q2X3. So I've now answered question 4, and again, this was part B of question 4. So now it's time to move on to the review for topic 5.2, Introduction to Rate Law. Here are some essential knowledge statements from the AP Chemistry course and exam description. Experimental methods can be used to monitor the amounts of reactants and/or products of a reaction over time and to determine the rate of the reaction. The rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to a power. And the power of each reactant in the rate law is the order of the reaction with respect to that reactant. The sum of the powers of the reactant concentrations in the rate law is the overall order of the reaction. And the proportionality constant in the rate law is called the rate constant. The value of this constant is temperature dependent, and the units reflect the overall reaction order. And then finally, comparing initial rates of a reaction is a method to determine the order with respect to each reactant. All right, now it's time to move on to the practice for topic 5.2. This is question 5. In question 5, we are given a balanced chemical equation, and it says the rate law for the reaction represented by the equation shown above is rate equals the rate constant K times the concentration of nitrogen monoxide squared times the concentration of chlorine. So with that rate law, they're telling us that this reaction is second order with respect to nitrogen monoxide and first order with respect to chlorine. Now, the question goes on to say that an experiment is set up in which the initial rate of disappearance of chlorine at 300 Kelvin is measured in different trials with various initial concentrations of the reactants. An incomplete data table from the experiment is shown below. So we can see that it's only in experiment 1 that we actually have a value for the initial rate of disappearance of chlorine. And in part A of this question, it says, based on the given information, calculate the value of the rate constant K, include units in your answer. So I'm going to take the numerical values from experiment 1, and I'm going to plug those values into our rate law expression. So we have rate equals the rate constant K times the initial concentration of nitrogen monoxide, which in experiment 1 is 0.0200 moles per liter. And as you can see, that value is squared in the rate law. And then I also have the initial concentration of chlorine, which is 0.0100 moles per liter. Now, when I do that math on the right side of the equation, 0.02 squared times 0.01, I get 4.00 times 10 to the negative 6, and so far, my units on that side of the equation are molarity cubed, because I have molarity squared times molarity. Now I have the rate constant K, but I don't know what that numerical value is at the moment, and I also don't know exactly what the units are at the moment. So on the left side of the equation, I wrote the value for the rate, the initial rate of disappearance of chlorine, and that is 7.80 times 10 to the negative 4, and my units are molarity per second. And you'll notice that sometimes when I write molarity per second, I write capital M/S, so molarity per second. But another way to represent molarity per second is to use that symbol you can see at the bottom of this slide, which is capital M for molarity, and then I have second to the negative 1 power. So second to the negative 1 power is the equivalent of 1 over seconds, or per second. So now that I've plugged in all of the numerical values from experiment 1 from the data table, all I have to do right now is to do the math to calculate the value of K and then make sure to include the correct units in my answer. So to get K on a side by itself, I'm going to divide both sides of this equation by 4.00 times 10 to the negative 6 molarity cubed. Now, when I do that math, it will be 7.80 times 10 to the negative 4 divided by 4.00 times 10 to the negative 6, and I get a value of 195. Of course, I have not yet included the units of the rate constant K in my answer, but that is the numerical value. So if I look closely at the units, I can see that there's molarity on top and then molarity cubed on the bottom. So I have molarity to the first power divided by molarity to the third power. That's going to give me 1 over molarity squared, or I can write that as molarity to the negative 2. But I still have to deal with the seconds. So the seconds would be seconds to the negative 1. So there is my answer to part A. The numerical value of the rate constant is 195, and the units are 1 over molarity squared and then 1 over seconds, or molarity to the negative 2 times second to the negative 1. Now I'm going to move on to part B of this question. In part B, it says calculate the expected value for the initial rate of disappearance of chlorine in trial 2 and in trial 3, and then write your answers in the table above. Now, there's one way that I could not use the rate constant. I could simply look for a situation of comparison. So what I could do is say that in comparing experiments 1 and 2, they kept the initial concentration of nitrogen monoxide constant, but they doubled the initial concentration of chlorine. And now I could remember that this is first order with respect to chlorine, so the rate is doubled. But what I'm going to do is simply take advantage of the fact that I already have a numerical value for the rate constant K. So go ahead and take a look at what I'm doing to solve in part B, the initial rate of disappearance of chlorine. You can see I'm using the rate constant. I'm using 195, and my units are molarity to the negative 2 times second to the negative 1. And now I'm using the values for experiment 2 from the data table. So initial concentration of nitrogen monoxide is 0.0200 moles per liter, and that value is squared because it's second order with respect to NO, and then times the initial concentration of chlorine, which is also 0.0200 moles per liter. So you'll notice that when I get my numerical answer, I still have units of molarity per second for the rate, but my value is 1.56 times 10 to the negative 3 molarity per second. So if I had simply doubled the initial rate value from experiment 1, then that's what I would have gotten if I had just multiplied by 2. But I'm going to go ahead and use the rate constant and plug in everything I know into the rate law to get my answers for part B. So in a similar fashion, when I move down to row 3 of this table, experiment 3, there's my rate constant again, 195, and my units are molarity to the negative 2 times second to the negative 1. I plugged in 0.0400 molar for my concentration of nitrogen monoxide, and that value is squared, times the initial concentration of chlorine, 0.0200 molar. And when I did that math, I got 6.24 times 10 to the negative 3, and my units again are molarity per second. So what I did was I used the rate constant and the initial concentrations of the reactants, and I plugged in all of those values into the rate law that I was given. All right, well, those are the answers to parts A and B of this question. So now it's time to move on to the next question. This is question 6. Now, as you look at question 6 and then you compare question 6 with question 5, you'll notice that there are some similarities. They both involve a data table. They both have to do with the initial rate of reaction. But a big difference between question 5 and question 6 is that in question 5, we were given the rate law for the reaction. But here in question 6, we are not given a rate law. In fact, in part C of question 6, we actually have to write the rate law using the experimental data to determine the order with respect to each of these reactants. So it's a little different here in question 6. The reaction between nitrogen monoxide gas and hydrogen gas is represented by the equation shown above. An experiment is set up in which the initial rate of formation of nitrogen gas at 300 Kelvin is measured in different trials with various initial concentrations of the reactants. Data from the experiment is shown below. So we can take a look at experiments 1, 2, and 3, and we have initial concentration of nitrogen monoxide is listed. We have initial concentration of hydrogen is listed. And then for experiments 1, 2, and 3, we also have the initial rate of formation of nitrogen gas. So let's go ahead and take a look at part A. It says a student makes the claim that this reaction is second order with respect to hydrogen. Do you agree or disagree with the student's claim? Show calculations using data from the table to justify your answer. So what we're going to do to determine the order with respect to hydrogen is something that was mentioned in a couple of the essential knowledge statements from the AP Chemistry course and exam description for topic 5.2, Introduction to Rate Law. So again, to determine the order with respect to a particular reactant, it says comparing initial rates of a reaction is a method to determine the order with respect to each reactant. So what I'm going to do is I'm going to look for two different experiments in which they held the initial concentration of nitrogen monoxide constant, but they changed the initial concentration of hydrogen. And so that means I'm going to be looking for a comparison of experiments 1 and 3. So notice that in experiment 1 and experiment 3, we have the same concentration of nitrogen monoxide, but we have a different concentration of hydrogen. That means we can focus our attention on how did the change in the initial concentration of hydrogen affect the initial rate of the reaction. So it looks like going from experiment 1 to experiment 3, the initial concentration of hydrogen was tripled or increased by a factor of 3. And now if I do that same ratio and proportion with the rates, I discover that that's also a threefold increase in terms of the rate of formation of nitrogen. So what does that mean? That means that it's first order with respect to hydrogen. So here's what I said. I disagree with the student's claim. Comparing experiments 1 and 3, the initial concentration of hydrogen is tripled while the initial concentration of nitrogen monoxide is held constant. The initial rate is tripled, so therefore this reaction is first order with respect to hydrogen. Now we're going to do a similar style of comparison for part B. So let's go ahead and take a look at part B. So the instructions in part B say determine the order of the reaction with respect to nitrogen monoxide. Show calculations using data from the table to justify your answer. So this time, I actually do want the initial concentration of nitrogen monoxide to be changed. And I would love to find an example where the initial concentration of hydrogen is held constant. And so what I'm going to do now is compare experiments 1 and 2. And the reason why I'm comparing experiments 1 and 2 is because, as you can see, it shows a change in the initial concentration of nitrogen monoxide while the initial concentration of hydrogen remains constant. So that means I can see how did the change in the initial concentration of nitrogen monoxide affect the initial reaction rate. As we go from experiment 1 to experiment 2, the initial concentration of nitrogen monoxide has been tripled. Now let's double check and see what happened to the initial reaction rate. So when I do that ratio, I can see it was not an increase by a factor of 3, but rather an increase by a factor of 9. So the initial concentration of nitrogen monoxide was tripled, but the initial rate of the reaction was increased by a factor of 9. So this does not mean first order with respect to NO. This is actually second order. So here's my answer to part B. Comparing experiments 1 and 2, the initial concentration of nitrogen monoxide is tripled, while the initial concentration of hydrogen is held constant. The initial rate is increased by a factor of 9. Therefore, this reaction is second order with respect to nitrogen monoxide. And so, as I had mentioned earlier, in part C of this question, they are going to ask us to write the expression for the rate law. So now that we know that this reaction is first order with respect to hydrogen, and this reaction is second order with respect to nitrogen monoxide, we can go ahead and write the rate law for this reaction. So in part C, it says, write the expression for the rate law for the reaction as determined from the experimental data. And so as you can see, I wrote rate equals, and then the rate constant K, times the concentration of nitrogen monoxide squared, because this reaction is second order with respect to nitrogen monoxide, and then times the concentration of hydrogen, which again would be raised to the first power. That's understood because this reaction is first order with respect to hydrogen. So there's my answer for the rate law for part C. And now in part D of this question, it says determine the value of the rate constant for the reaction at 300 Kelvin. Include units in your answer. Now, technically, you could pick experiment 1 or experiment 2 or experiment 3, and you would get the same numerical value for the rate constant, but I'm not going to show you all 3 of those calculations. You can just take my word for it. So I'm going to go ahead and to determine the value of the rate constant, I'm going to just choose the data from experiment 1. So there's my rate law. So rate equals rate constant K times initial concentration of nitrogen monoxide squared times initial concentration of hydrogen. And the only thing that I don't know in experiment 1 is the value of the rate constant. So what I'm going to do is plug in everything I know in terms of the numerical values. So I have 7.80 times 10 to the negative 3 molarity per second. And that equals the rate constant K times the initial concentration of nitrogen monoxide squared times the initial concentration of hydrogen. Now, when I did 0.03 molar squared times 0.03 molar, I got 2.70 times 10 to the negative 5, and my units are molarity cubed. I'm going to go ahead and solve for K, and I will get a numerical value of 7.80 times 10 to the negative 3 divided by 2.70 times 10 to the negative 5, which equals 289 when I did that math on my calculator. And because I have molarity times seconds to the negative 1 divided by molarity cubed, I actually get the same units of the rate constant here in question 6 part D that we saw in question 5. And I think it's because both rate laws happen to be third order overall. So it was the same units for the rate constant K, just coincidentally. So there's my answer to part D of this question. The rate constant is 289, and my units are molarity to the negative 2 times second to the negative 1. Now let's go ahead and take a look at part E of this question. Remember that in experiment 4, the initial rate of formation of nitrogen gas was unknown. That's why there was a question mark. So now in part E, it says, calculate the initial rate of formation of nitrogen in trial 4 in units of molarity per second. So all we have to do is plug in the rate constant, which is 289 molarity to the negative 2 times second to the negative 1, and then times the initial concentration of nitrogen monoxide squared times the initial concentration of hydrogen. So when I do that math, I will get the rate, and my units will be molarity per second. So 289 times 0.0750 squared times 0.0750 gives me a value of 0.122, and my units are molarity per second. All right, we've gone through parts A through E of question 6. So now there's only one more part left in this particular question. This is part F. Now, as you can see in part F, there are no calculations. It's more of an explanation. It says, when this reaction occurs at a higher temperature, the value of the rate constant K increases. Now, based on collision theory, explain why the value of K increases with temperature. So this is what I said for my answer to part F. I said the value of K increases at a higher temperature because the reactant particles have greater average kinetic energy. Now it does say based on collision theory, so you'll notice that I did use the word collide in my explanation here. I said they have greater average kinetic energy and they collide with greater frequency. And a greater fraction of the particle collisions have sufficient energy to overcome the activation energy of the reaction. Now, as you read my answer to part F of question 6, you might wonder, was activation energy a topic that was mentioned earlier in this video? And actually, the answer to that question is no, it has not been mentioned. So what I will tell you is that technically, activation energy was not included in the essential knowledge statements for topic 5.2. But if you look at this next slide, you will see that later on in a future episode of AP Chemistry Review and Practice, when I talk about topic 5.6, which is reaction energy profile, I will mention the activation energy for the reaction, and I will talk about the activation energy that is needed by the molecular collisions to reach what is called the transition state. So that's a little preview of things to come. But since we are done with question 6, now it is time to move on to the review for topic 5.3, concentration changes over time. Here are some essential knowledge statements from the AP Chemistry course and exam description. The order of a reaction can be inferred from a graph of concentration of reactant versus time. If a reaction is first order with respect to a reactant being monitored, a plot of the natural log of the reactant concentration as a function of time will be linear. If a reaction is second order with respect to a reactant being monitored, a plot of the reciprocal of the concentration of that reactant versus time will be linear. And the slopes of the concentration versus time data for 0th, first, and second order reactions can be used to determine the rate constant for the reaction. Now, you'll notice that there are 3 equations that are listed here. So I'm going to go ahead and show you. This is the second page of the AP Chemistry equations and constant sheet, and you will get this on the AP Chemistry exam. I'm going to give you a closer view of the kinetics section. And although they're not labeled, that first equation refers to 0 order. That second equation applies to first order. That third equation applies to second order. And so that last equation for half-life, that is only applicable for first order. So this is, again, a portion of the AP Chemistry equations and constant sheet that relates to Unit 5, kinetics. So again, you can see that these equations that I'm highlighting on this slide are also featured on the AP Chemistry equations and constant sheet. And the next essential knowledge statement says, half-life is a critical parameter for first-order reactions because the half-life is constant and related to the rate constant for the reaction by the following equation. So half-life equals 0.693 divided by the rate constant K. But that's only applicable for first-order reactions in which the half-life is constant. And then finally, the last essential knowledge statement for topic 5.3 says that radioactive decay processes provide an important illustration of first-order kinetics. All right, now it's time to move on to the practice for topic 5.3. This is question 7. In question 7, we are given a data table, and it says, the decomposition of substance D is studied by monitoring the concentration of D over time, and the data from the experiment is shown in the table above. Which of the following is the rate constant K of the decomposition reaction? So we can see in the data table that we have concentration, which goes from 6.48 moles per liter all the way down to 1.02 moles per liter. And then we have the time, and it goes from 0 minutes to 40 minutes. And I'll just remind you what I had mentioned earlier. Half-life is a critical parameter for first-order reactions because the half-life is constant. So we don't know if this is first order, second order, or 0 order, but if we can start by looking for half-life, then maybe we can at least make a conclusion about whether the half-life is constant over time or not. So I'm going to begin with 6.48 moles per liter. And so what number is half of 6.48 is 3.24. Now it looks like in the data table it takes 15 minutes to go from 6.48 molar to 3.24 molar, but that's not enough for us to conclude that the half-life remains constant over time. That's only one half-life period. Let's look for the next half-life period and see if, in fact, it does remain constant over time. So what number is half of 3.24? And that would be 1.62. Okay, so now we can say with confidence that the half-life is constant over time. Why? Because it takes 15 minutes to go from 6.48 molar to 3.24 molar, so that's one half-life period. But then as we continue, it takes another 15 minutes to go from 3.24 molar to 1.62 molar. That's another half-life period. So what we can say in question 7 is that the decomposition of substance D is, in fact, first order with respect to D. And the reason we can say that this is first order with respect to D is because the half-life, which happens to be 15 minutes, does in fact remain constant over time. So if that particular equation, half-life is equal to 0.693 divided by the rate constant K, can be used when the half-life is constant, and that's first order kinetics, I'm going to go ahead and solve for the rate constant K. So right now I have half-life equals 0.693 divided by the rate constant K. I'm going to rearrange this equation. So the rate constant K is equal to 0.693 divided by the half-life, which we have determined from the information in the data table to be 15 minutes. So 0.693 divided by 15 minutes gives me a value of 0.0462, and my units are inverse minutes. So that is the value of the rate constant, which means that the correct answer to question 7 is choice B. Now let's take a look at question 8. Now in question 8, we are not looking for half-life like we were in question 7. What we're looking for in question 8 is a linear relationship. So it starts off by saying that compound X is known to decompose over time. To study the reaction, a chemist monitors the molar concentration of compound X at a temperature of 350 kelvins, and after collecting and analyzing the data, the information in the following data table was recorded. So we can see that there's time going from 0 seconds to 300 seconds with data for concentration, the reciprocal of concentration, or the natural log of the concentration. Now, all of these numbers have been generated for us, but we have to generate some graphs. So as we look at part A of question 8, it says the data in the table above can be plotted on the graphs below. The data for natural log of concentration versus time has already been plotted on the graph at the bottom of this page. But we have to plot the data for concentration versus time on the left graph. And then we have to plot the data for the reciprocal of concentration versus time on the right graph. So I'll start with concentration versus time. And so the first concentration I see is 12.5 moles per liter at a time of 0 seconds. So I'm going to put a dot on the graph at time 0 for 12.5. Now I have some more data points to plot. So at 50 seconds, it looks like it's approximately 8.33. And then at 100 seconds, it looks like it's 6.25. At 150 seconds, it's 5. So I'm adding points as I go on this graph. And then at 200 seconds, it's about 4.167. At 250 seconds, it's 3.571. And then at 300 seconds, it's 3.125. Now, I plotted this data. It doesn't look like a straight line or a linear plot. So hopefully if we get a linear relationship, it's going to be with the next diagram that we generate, and that would be the reciprocal of concentration versus time. So the first data point at time 0 seconds is 0.080. So I'll put a dot on the graph on the y-axis at 0.08. And now when I go to 50 seconds, it's 0.12. And at 100 seconds, it's 0.16. At 150 seconds, it's 0.2. This is looking like a straight line. I'm going to keep going. At 200 seconds, 0.24. At 250 seconds, 0.28. And at 300 seconds, 0.32. So it looks like numerically, every 50 seconds, the value of the reciprocal of concentration is increasing by a unit of 0.04 inverse molarity, or liters per mole. So every 50 seconds, that value increases by 0.04, and that does look like a nice straight line. So the natural log of concentration versus time has a little bit of a curvature to it. The concentration versus time graph that we did is also kind of curvy, but then we have a nice straight line for the reciprocal of concentration versus time. But what does this mean? Well, in my video for topic 5.3, I had presented this summary table. And so what you can see in this summary table is 0, first, and second. So 0 order, what does a graph of concentration versus time look like? It's a straight line, whereas first order and second order is a curve. And then it talks about half-life, where only first order has a constant half-life. And then the next row of the table says what type of graph should produce a straight line. And so if we get a linear plot for the reciprocal of concentration versus time, then we can say that this would be second order with respect to that reactant. This takes us straight into part B of this question. So we've done the graphs, and it says determine the order of the decomposition reaction with respect to X. Again, if a 1 over the concentration, or the reciprocal of the concentration versus time, is linear, then it's going to be second order. So that was my answer to part B. The decomposition reaction is second order with respect to X because the plot of the reciprocal of the concentration of X versus time is linear. Now, you may remember that we only stopped at 300 seconds, but there was another data point with a question mark. It says in part C, the chemist had monitored the molar concentration of compound X from 0 seconds until 400 seconds. This was not on the graph. Calculate the expected value for the concentration of X in units of mole per liter at 400 seconds. So if we look at this particular equation, this is the second order equation. This is where that linear relationship comes from. The linear relationship of the reciprocal of concentration, where 1 over the concentration at some time t minus 1 over the initial concentration at time 0 is equal to k times t. Now, we could actually solve for the rate constant if we wanted to, but what I'm going to do is just simply look at the connection of the top to the bottom, and I realize that as I go from top to bottom in this column, the value of the reciprocal of the concentration increases by 0.04 units every 50 seconds. So 0.08, 0.12, 0.16, 0.20, etc. But that's every 50 seconds. Now let's take a look at the bottom of the table. We're not going from 300 to 350. We're actually going from 300 seconds to 400 seconds. That's a bigger jump than all the other intervals of time in this table. So I just added this information. In this column, the value of the reciprocal of the concentration of X actually increases by 0.08 units every 100 seconds. So if I go from 0 to 100, then to 200, and then to 300, then to 400, I'm actually making that value change by 0.08. So what is 0.32 plus 0.08? That's what I'm looking for, and that works out to be 0.400. Now that's not the concentration, that is the reciprocal of the concentration. But they want to know the concentration, which would mean what's 1 divided by 0.4. And so 1 divided by 0.4 is actually 2.5. So the answer to part C The chemist had monitored the molar concentration of compound X from 0 seconds until 400 seconds. Calculate the expected value for the concentration of X at 400 seconds, and the answer is 2.50 moles per liter. All right, now it's time to take a look at question 9, and this is another decomposition reaction. In question 9, it says, a sample of CH3, CH2, NH2, which is known as ethylamine, is placed in a previously evacuated reaction vessel at 773 Kelvin, where it decomposes according to the equation shown above. An experiment is carried out to measure the rate of the reaction, which is first order, with respect to this ethylamine. So we don't need to determine whether it's 0 order, first order, or second order. They're telling us that this is first order. But we're not going to use half-life to do a calculation in part A. We are given the initial concentration of ethylamine, and so that works out to be 2.35 times 10 to the negative 3 molar. And then we're also given the concentration of ethylamine after 20 minutes, and that's 3.60 times 10 to the negative 4 moles per liter. So 20 minutes is not the half-life. It is simply a future point in time in which the concentration of the reactant has decreased. Now, they say calculate the rate constant for the reaction at 773 Kelvin, include units in your answer, so you might be a little stumped as to how we can do this problem. But remember, you have an equation sheet. And so they told us it was first order, so no, we're not going to use the half-life equation, but we can use this particular equation, which says the natural log of the concentration at time t minus the natural log of the initial concentration at time 0 is equal to negative k, the rate constant, times the time. If we plug in the information that we're given into this particular equation, we know everything except for the rate constant k. All right, so this is how I set up that equation. I put in to my equation the concentration at time 0 of 2.35 times 10 to the negative 3 moles per liter. So that's my concentration at time 0. And then I put the concentration at 20 minutes as 3.60 times 10 to the negative 4. And since the time is 20 minutes, I put that in for t. So now all I have to do is do the math and solve for k. So I'm going to go ahead and show you my work. So this is what the numbers I got after I took the natural log of those two concentration values. And then I did some more math. And eventually what I got down to was 1.876 equals the rate constant k times 20 minutes. And so in this question, we have to not only solve for the numerical value of the rate constant k, we also have to include units with our answer. So the units are going to be inverse minutes. So it's 1.876 divided by 20 minutes, and I get 0.0938, and my units are inverse minutes. So the units of a first order rate constant will always be inverse time. It might be inverse seconds, inverse minutes, inverse hours, but the units of a first order rate constant will always be inverse time. All right, well, that's the answer to part A. Now let's take a look at part B, which says calculate the initial rate in molarity per minute of the reaction. So there's our first order rate law. So rate equals the rate constant K times the initial concentration of the reactant, which we already know that value. And since we just calculated in part A the rate constant K, that means that we can go ahead and put in those two values. So the answer to part A was 0.0938 inverse minutes. That's my rate constant. The initial concentration was given to us in this problem as 2.35 times 10 to the negative 3 moles per liter. So rate equals rate constant times initial concentration, and when I do that math, I get 2.20 times 10 to the negative 4, and my units are molarity per minute. So that is my answer to part B. Now, we haven't done half-life until now. This is going to be part C of question 9. It says calculate the half-life for the decomposition reaction at 773 Kelvin. So how do we get the half-life? Back to the equation sheet, and we can see that the half-life for a first-order kinetics situation is 0.693 divided by the rate constant. So 0.693 divided by 0.0938 inverse minutes. And when we do that math, we get 7.39 minutes. And so that is the half-life for the decomposition reaction. All right, well, that is the last part of question 9. So now let's take a look at question 10. In question 10, it says the data from a kinetics experiment can be used to determine the rate law. Which of the following choices has correctly identified the rate law associated with the graph of experimental data for the decomposition of substance Q? Now I can see that in choices A and B, it's a linear plot with concentration versus time. And in choices C and D, it's a linear plot with the reciprocal of concentration versus time. And then we have rate laws, and the rate equals K. Well, that would be a zero-order rate law. But the rate equals K times the concentration of Q, that would be a first-order rate law. So let's see which graph matches the rate law correctly. Now, because choices A and B show concentration versus time as linear, and there's that summary information that I showed you earlier. So if I see concentration versus time, and it's linear, then that would be zero-order kinetics. So I'm going to label the first two graphs as zero order. Now, what about reciprocal of concentration versus time? Well, that would be second order if that particular plot is linear. So reciprocal of concentration versus time is linear, it would be second order. Now, onto the rate laws that are listed at the bottom of this table. Rate equals K would be zero order. Rate equals K times the concentration of Q would be first order. And so hopefully now you can see that the correct answer to question 10 is choice A, because it's the only one that matches the graph of what order that particular rate law is. So it's zero order, zero order. Everything else is incorrect. All right, well, hopefully that makes sense. And now let's take a look at the last question in this packet. This is question 11. So here in question 11, we have a data table, and it says a sample of substance XY was placed in an evacuated container, and a decomposition reaction occurred. And the concentration of XY was measured during the reaction and recorded in the table below. So like we saw earlier with question 8, we are looking for a linear relationship. So which data set shows a linear relationship versus time? I'm going to start with concentration versus time. And I'm going to take the difference. So 8 minus 6.89, 1.11. 6.89 minus 5.93, 0.96. 5.93 minus 5.10, 0.83. 5.10 minus 4.39, 0.71. So that is not looking like a regular interval. That is not linear. Let's move on to the natural log of concentration versus time, and we'll see if that's linear. 2.08 minus 1.93, 0.15. 1.93 minus 1.78. Oh, look at that. 0.15 again. 1.78 minus 1.63. Also 0.15. And then 1.63 minus 1.48. Again, same difference, 0.15. So this is a linear relationship. And then just to confirm that the reciprocal of concentration is not linear, I'll do a difference of, so 0.145 minus 0.125, that's a difference of 0.020. And then here's the next difference, 0.024. Here's the next difference, 0.027, and the last difference, 0.032. So again, not a linear relationship. Well, now that we know that the plot of natural log of concentration versus time is linear, it says, based on the experimental data, which of the following represents the order of the reaction and the value of the rate constant K. So if the natural log of concentration versus time is linear, that means first order kinetics. So the correct answer to question 11 is first order, which means it's either A or C, so we can eliminate choices B and D. Now, what about that rate constant? Well, the rate constant can be determined from the linear graph. It's the absolute value of the slope of that linear plot. So the slope would be rise over run. That would be the change in the y-axis, or the change in the natural log of the concentration, divided by the change in the x-axis, the change in time. So every 30 seconds, that plot decreases by 0.15. So every 30 seconds, that change is 0.15 for that linear plot. So 0.15 divided by 30 is 0.005, or 5 times 10 to the negative 3, and my units are inverse seconds. Now, you might say that, is there another way we could do this calculation if we use the equation sheet? And yes, you could use that natural log equation. You could just take 2 points. So I'll take the first 2 points, and I've taken the natural log of xy, or actually it's given to me in this problem. So 1.93 minus 2.08. That's the difference in 2 time periods. That's 30 seconds. And again, I would get the same answer. I would get 0.15 divided by 30 seconds, and I get that answer. So the correct answer to question 11 is that it's first order, and the rate constant is 0.0050 inverse seconds. So that means that A is the correct answer to question 11. Now, since this was the last question in this packet, it is now time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice for you is, if you need more practice problems on the topics 5.1 to 5.3, then you can review the information in my video for those topics. And there's that link. It's also in the video description area. My next piece of advice is to read the question carefully and make sure that you are answering the question that is being asked. Now, when the question requires a calculation, you must show your work, show the setup for your calculation in order to receive credit for your answer. And if you are asked to explain why each of the following experimental variables increases the reaction rate, make sure that collisions between reactant particles are included in your explanation. For example, suppose that you increase the concentration of a reactant, assuming that the reaction is not zero order with respect to that reactant. Well, the rate increases. Mention that it increases the frequency of the collisions between the reactant particles. If you increase the surface area of a solid reactant, again, you are increasing the frequency of the collisions between the reactant particles. If you increase the temperature of the reaction, well, you're going to increase the frequency of the collisions, the average kinetic energy of the collisions, and you increase the fraction of collisions that have enough energy to overcome the activation energy of the reaction. And if you add a catalyst to the reaction mixture, well, what you're doing is you're providing an alternate reaction pathway with a lower activation energy. So I will have more to say about things such as the activation energy, the energy diagram, and the catalyst in a future episode of AP Chemistry Review and Practice. These are all topics that are still in Unit 5, Kinetics. My next piece of advice is related to stoichiometry and coefficients. The coefficients from the balanced chemical equation for the reaction can be used to convert the rate of appearance or disappearance of one substance into the rate of appearance or disappearance of another substance. But even though the math might be simple, not only should you show your work, make sure to set up a proper conversion factor based on the mole ratio, and if you use units, then you minimize the chance of making a mistake. So always include your units, especially when there's potential for a mistake because the math is so simple. Assuming that there is a homogeneous reaction mixture, for example, a gas mixture or an aqueous solution, there are only two common laboratory situations in which a change in the experimental conditions would cause the value of the rate constant K to be affected. So when could the rate constant K be affected? A change in temperature or the presence of a catalyst. So, for example, suppose we have a first-order rate law in which rate equals K times the concentration of A. Now here comes the first change. You decrease the concentration of A at constant temperature. The initial rate decreases, but the value of K remains constant because the temperature did not change. Now, what if we go in the opposite direction? What if we increase the concentration of A at constant temperature? Well, the rate will increase, but again, K remains constant because we are at constant temperature. And if you decrease the temperature, the rate would decrease, but now because you change the temperature, K would also decrease. If you increase the temperature, the rate would increase, and again, K would increase because it's affected by temperature. And then finally, if you added a catalyst, well, the rate would increase, but since you're only adding a catalyst and you're not changing the concentration of the reactant, something has to increase. And so the value of K would increase if you add a catalyst. So just wanted to mention those scenarios. So it is possible for the rate constant to change, but typically that would only be if you have a catalyst or a change in temperature. All right, this question, I'm not going to go into all of the details of this question, but I just want to remind you of some common mistakes, was from 2025. So this comes from question number 2, part C, on the free response section of the 2025 AP Chemistry exam. And again, you'll see all of the links in the video description area for 2025, 2024, 2023 that I had mentioned in this episode. So what happened was they had to explain how the data in the table support the conclusion that the reaction was first order with respect to this ascorbic acid. And they also had to calculate the value of the rate constant K and include the units. So if you're given a data table similar to the one shown above that lists multiple trials, the initial concentration of each reactant, and the initial reaction rate, you probably know what they're going to ask you. They're going to talk about the order and the rate constant, but be careful to avoid the following mistakes. Now, these mistakes that I'm mentioning, they were observed from students who answered question 2, part C on the 2025 AP Chemistry exam. So in part CI, students did not earn the point for their response if they were too vague. So for example, all they said was something such as, quote, when the concentration is doubled, the rate is doubled. Now, if you answer a question like that, you should include which trials are being compared, which reactant concentrations stay constant, which reactant concentrations are changing, how they are changing, and also how the initial reaction rate is changing. So be specific. And then another kind of careless error was that the rate constant was 4.55 times 10 to the negative 4, and so students just wrote down the 4.55 part. They forgot the times 10 to the negative 4, and they also made the mistake of either omitting the units for the rate constant or they wrote incorrect units. All right, this is a summary of the units for the rate constant for some rate laws. So for example, assuming that we have molarity per second for the reaction rate units, if it's 0 order, then K would be molarity per second. If it's a first order rate law, then the units of K are just inverse seconds or inverse time in general. If it's a second order rate law, then the units of K are molarity to the negative 1, seconds to the negative 1. So if it's second order rate law, molarity to the negative 1, second to the negative 1. And then as we saw in this episode, in this lesson, if it's a third order rate law overall, then the units of the rate constant are molarity to the negative 2, seconds to the negative 1. Just a summary of, if you have to include the units for the rate constant, just be careful to include the correct units of that rate constant. And then this was a table that I had mentioned earlier in this video, in this lesson. So a summary of important information that's relevant to topic 5.3 with respect to what does a graph look like of concentration versus time? Does the half-life remain constant over time? What type of graph should produce a straight line? How do you determine the value of the rate constant K from the linear graph? And then again, what are the units of the rate constant? All right, so we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 5.4 to 5.7. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.